So relational tables do have a lot of advantages, but you have to be careful how you structure them. If you don't put them together right and then use them correctly, you'll end up with a bunch of problems. It'll be more trouble than it's worth. And so you have to be careful about a few things. And one of the things is to make sure you get your tables into normal forms and you keep them in these normal forms. And to do normal forms, you got to understand this concept of what's called functional dependencies. So there are all these good reasons for normal forms we've gone over. The thing is, we make sure that our tables are broken up from our flat file, as I show here, into a normal form that's called a third normal form. Now, there are various levels, first, second, and third. There's fourth and fifth. I think there may be higher normal forms, but typically we go to at least to the third normal form. And why do we do this? Again, to isolate the data into the pieces that are non-redundant, related to each other in ways that can be linked back together. So here's a flat file. It's a good example. It's land records, and I have parcels, and the parcels are in townships with aldermans and township IDs and township names and town hall addresses, and then there are owners, and there can be multiple owners for the parcel. Each of the owner has a unique ID and a name and an address. Now, parcels can have multiple owners, so I might have 2, 3, 4, 5 owners for a parcel, and you'll see that in these repeat columns, this owner ID, owner name, owner address, owner ID, owner name, owner address again. So we have owner ID 122, which is Devlin, who lives at 123 Pine, and that's for this parcel 2303. And we have owner ID 337, Yamani, at 72 Lotus. So we could have multiple owners. Some parcels just have one owner. So this is a flat file, a typical sort of set of issues, the ones we talked about having. You could have basically repeat columns, you could have redundant data, you could have empty data, right? Yamani is listed several places here because Yamani owns several parcels. And these blank entries, you don't know how many of a type there are, how many owners, by just looking at it for a parcel. And so we want to get out of this flat file into a more normalized form. Now, often you don't have to create normal forms for your data. You're just using data somebody else created, and there's lots of data that are in normal forms. Soils data are structured in these normal forms. If you look at the U.S. Soil Survey data, the SURGO data, they have basically a bunch of data tables that are broken into normal forms, and they show you how to recombine them to get the information you want. So on the texture, on crop cover, on engineering properties, on all sorts of things you might want to get for soils data that go with a soil map. Census data are in normal forms with various IDs that are used as keys in some tables to link to foreign keys in other tables, and so you build up the information you want. And a lot of data from other agencies are tied to census data through their normal form. So it's a standard way of presenting large data sets, complicated data sets, and so it's good to understand how they're put together, and that'll help you then in using these. Now, key to normal forms and to relational data are keys, those columns that uniquely identify the rows in the table. Now, there can be many candidate keys, many either single or multi-column combinations that will uniquely identify a row. We're striving for the smallest keys, so the fewest number of columns that we can for a table, and it's often one. And we identify then that as the primary key that we'll use to index this table, to connect this table to other tables. There's also a concept called functional dependency. It's described in the book. So it basically means if I know the value of one column, in this case the key column, I can tell you the value of every other column in that row. So the great thing about something like a social security number or a student ID number, if they're uniquely assigned to the individual, is once I know that student ID number for the student, I know the rest of the relevant information if I'm using that student ID number as a key. So your first and last name, your address, the year you first entered the university, any other information that's associated with that person I can put in a table, and then that will be uniquely identified. Now notice it doesn't mean that, for example, if I have a value like the date you entered the university, for a key value, it tells you that basically when that person entered the university, there can be other people that have that same value. It just for that particular row, that row is uniquely defined. I won't find a key anywhere else that has basically different values for any of the columns. So typically what we're striving for in a key is it only occurs once in a column and everything else behind it, I know what it is. The problem is there can be non-key attributes. So we can have other things and then they can have things that are functionally dependent on them. So I might know something about a particular flange, right? It's a piece of equipment. And any one of those flanges are always made of the same kind of material. It's an aluminum flange. So if I know it's that flange type, I know its material is aluminum. There may be several different flange types in that class, but I know that material is aluminum. Now, that flange type might not be a key, but there's something functionally dependent on it. And we'll have some examples that'll kind of show this. Keys join tables, they relate things, and we want things so that everything in a table is functionally dependent on the key, right? We break our tables up, and we're often breaking them up in a way that gets them into sort of their natural groupings, plus another set of tables to join the tables together. You might think about our example here for the parcels. We have information here on people, so I'll expect to get a person table out there. We have information on parcels, there'll be a parcel table out there. And information on townships. So I expect at least 3 tables because there's 3 kind of organic different things here. The parcel, the person, and the township. And then I'll get some tables that'll join those together. So just looking at them and looking at most problems, you can identify what are the organic groupings, what are the organic pieces that kind of that you'd split up that have related sets of information. So we break up our tables such the data are naturally grouped, and each table has a key, and we put them in this third normal form where everything is functionally dependent on the key, and there are no what we call transitive functional dependencies. So there's no dependent on dependent things. Again, hopefully that'll be clear. Right? Here we have examples of a key I'll go through. So state can be a key in this table because it's unique. Arkansas, Alaska, Alabama, Arizona, Oregon, Wyoming. But south can't be a key, can it? Right? Because I have multiple values of south, right? Multiple values of west. West large, west small. So if I know the value is west, I don't know what all the other things are. It doesn't uniquely identify this row, right? Size, population. So region, size, and population can't be keys, right? So what are functional dependencies? The functional dependencies, if you know the value of column A, you can automatically know the value of column B. This means column B is function dependent on column A. So everything's going to be function dependent on the key. But there can be other functional dependencies in the column. So for example, I can look at this class. Is size functionally dependent on class? That means if I know the value of class, I know the value automatically of size. I don't have to look it up. So there's A large. So maybe, right? I mean, if I only look at A, sure, if I know class, I know size. BR small, BR large, nope. Size is not functionally dependent on class because knowing the value of BR doesn't tell me the value of class as BR, doesn't tell me the value of size. It can be large or small. So again, look at class and color. A blue, A red, nope. Color isn't function dependent on class, right? A round, A square, nope. Shape isn't function dependent on class. So I can look at these and see if all the way down for every value, and that would be entirely in the table or in my universe of expected values, that if I know one value in a table, I'll automatically know another value in another column. Then that's the functional dependency. So we can look for them. We often define an item so that it serves as a key, our social security number, our university ID number, and parts manufacturing number. So that's automatically a key, and everything in the table is functionally dependent on it. because that's the key. So it's pretty straightforward for a lot of tables. We have to make sure that we keep our functional dependency intact in all our analysis and all our manipulations. That's what we call maintaining referential integrity. We want to make sure that we don't mess up that key by entering duplicate copies of our key value in that key column. So there's often protections against that in data entry, but when you're using data, you have to be careful you don't mess it up. You don't enter a second copy. Often there are issues in databases when that happens. So if you've ever been messed up because it's not in the system where you're getting duplicate records, it's because they didn't trap that error, right? So functional dependency is type. If we know type, do we know class? So is class function dependent on type, right? Type 1, that's A, right? You don't even have to check if there's only an individual value. If there are multiple values, like there are multiple 2's here, 2BR, 2A, no. So we know that if we know type, we don't know class, because here we know type is 2 and it's BR, and here we know type is 2 and it's not BR, right? So that's not serving as our functional dependency. If I know type, I don't know class, right? So I can answer no. If I know type, do I know size? 1 large? Well, I don't really check the ones. 2 small, 2 small. So far, so good. 2 small. Hey, there's multiple 3's. 3 large, 3 large. And then there's just 1 4 and 1 8. So yeah, if I know type, I can tell you what size is. Now I'm testing for it in this table to give you the idea of what a functional dependency is, but in real life, when you're putting together a data set, what you have to ask yourself is, if I know the value in one column, will I automatically know the value in the other column? Does it come in lockstep? So maybe I have a vegetation type, and I know in that vegetation type I can have, by the definition of the vegetation type, 3 species, right? So if I know the vegetation type, then I'll know a component species. So you have to basically look at how your data occur and say, oh, if I know A, will I know B? If I know the value in column A, no matter what that value might be, will I automatically know the value in column B or in column C? So the data have a functional dependency in their structure and how you put them in. You can test for it like I'm showing you in this table, but if you're using this in a real database, you have millions of records. You can't look for every value. You have to think in advance, well, as the data are assigned, is that a functional dependency that can occur, right? You can go through more tests for type and size and all these others. So items that uniquely identify the rows. What single items can be keys here? Well, most of you might say, oh, look, PID. This PID 1, 3, 5, 7, 9, and then there's a null, but that doesn't copy on anything else. The problem is the null value eliminates this column as a candidate key, as a possibility for a key. You can't have null values because they match everything and they match nothing. So you can't have nulls in your primary key, and so you can't enforce the functional dependencies. It's kind of like the notion of infinity. It doesn't really match anything, and it's kind of its own special case. So nulls you can't have as a member of a key, can't appear. If it does, if you've made a mistake, or your data will likely have errors in it, right? So in this case, there's no single candidate key, so it's what pair of items can serve as a key. So you have to look at, well, if I know this is B and this is OR, do I know this is 1? Well, there's only one copy of B and OR, sure, so that's true. Here I have really the only duplicates are A and BL, and 1 and 9 will both be occurring when I have A and BL, so this doesn't serve as a candidate key. I can't use PID, right? So here's A and 1 and A and 9. Well, those are both 65. All of these are unique, right? And so these two, O, S, E, L, and num-t will serve. And there may be other values that will serve. So, O, cell, and num-t, CLR, and num-t, this one, SPLM, and num-t. Those will all serve as candidate keys. So I could pick one of those pairs. Now, in splitting up databases, you typically, as I said, break the tables up, and most of the columns just have a single item is a candidate key that you'll use as the primary key. That'll be the key you'll choose for that table, and it's pretty straightforward. It's unique. But there are always some tables that have 2 columns as the key, sometimes 3 columns, and those are usually used to join other tables back together in the way you want the information. So let's walk through our table here that's unnormalized, right? It's the one I showed at the start with the parcel IDs and the owners and the town hall information. And the first thing we want to do to get it to first normal form is get rid of these repeat columns. Now here the repeat columns have the same names. They don't have to have the same names, but they have to store the same type of information, right? This could be owner name 1, owner address 1, owner ID 1, owner ID 2, owner name 2, owner address 2. So you could have these various ones linked 1, 2, 3 different names, but the idea is they're storing the same kind of thing. I could store the information here or the information here without any loss of clarity if these 2 people were to buy a parcel together. So these are the same or duplicate kinds of data, although they're not duplicate entries. So what I do is I say, well, I have these 3 that really are associated with owner. What I'm going to do is copy all the information here that's not an owner name, owner ID, the ownership stuff, and put it in a column with the stuff that's unique. So here I have Devlin, Yamani, and Prestovich for 203. Well, I'll make 3 rows that are this 2303, one for Devlin, one for Yamani, one for Prestovich. So I'm sort of cutting off the extra and I'm adding extra rows. So I'm making duplication. You might say, well, that's kind of silly. I'm not really doing anything except maybe saving this empty space. In some data sets, that might save 90% of the space that's taken up and going from a flat file to a first normal form. But usually we don't stop there. We want to get rid of this redundancy. It's easy to code this, but there's still lots of redundancies, and it would be excessively slow because of those redundancies. Well, second normal form. This is where we start using an idea about functional dependencies. What we want to do is first go to first normal form, and then we split that table into tables where every non-key attribute is function dependent on the primary key. So we want basically one primary key, and there'll be multiple tables like this. These end up being the tables that are those organic groups. So again, what I'll do is I'll take this and I'll split it up into several tables. And this is the kind of the murky part, is it ends up being 3 tables here. 2 of the tables are pretty straightforward. One associated with the parcels and one associated with the townships, or maybe with the people. But then you'll get a sort of joining table to join those 2 together, right? So again, this functional dependencies, I have to identify them. In this data set, you should go through it if you don't understand this, but if I know parcel ID, I know alderman. If I know parcel ID, I know town hall address. If I know parcel ID, I know township. Parcel ID, I know township name. So look back at the definition of parcel ID and at this table and say, and verify that that's true, that those functional dependencies, that all these things are dependent on parcel ID. So what I can think about is having a parcel ID and then having all this stuff in that table, right? I can look for other functional dependencies and I end up finding another set of functional dependencies that are around the owner. I know owner ID, I know owner name, and owner address, right? Once I fix this, I have this. And that makes sense. So here I have the parcel ID and then the alderman, the township name, the township ID, and the town hall address. So there's these 2 tables. One's associated with parcels, kind of the organic stuff associated with it, and one's associated with owners. And then I have this third one that comes through that I develop to connect these 2 tables. It saves basically the parcel to owner connection, right? So I have this owner and this parcel. These 2 columns basically are have to be used to make this thing a key, right? Because I have multiple values of 2303. It really, what I'm doing is creating this 2-column connection table that is sort of the remaining things to get these 2 that are function with nothing functional dependent to get a key, to get a standard key. So there's just this sort of table, and these are the ones that are the hardest to understand, that you have to create, that are the connecting tables that have multi-column keys and are there to preserve the relationships between the other two tables, right? It's the only way to sort of connect the land records table to the owner ID table. And whenever we split a table off and get either an additional column or an additional table for that relationship. So these two are pretty straightforward. Yeah, I have this parcel stuff and I have this owner stuff. And then this one is usually sort of a connection between those two tables you split that saves the information that connects them. And a lot of times you'll get those things. If you see these kind of weird tables that are mostly just the keys of other tables, their job is to connect the tables together. So, third normal form gets rid of what we call transitive functional dependencies. And this is a little complicated concept. You might have to read the information in the book a couple times. But transitive functional dependencies, if B is dependent on A and C is dependent on B, then we know C is dependent on A. And what we want to do is split this up so that there are no transitive functional dependencies. We have to identify those. Now, that means we need sort of three things in this train of transitive functional dependencies. And what we want to really do is identify things that are dependent in our tables, function dependent on non-key attributes. That's really how we get rid of these. If you find things that are dependent on non-key attributes and split those tables. If the table doesn't have anything that's dependent on a non-key attribute, I don't have to split the table further. But if I find something that's dependent on a non-key attribute, then I have to split the table. And so you'll sometimes see these tables. Now there's nothing that's dependent on a non-key attribute, because if this is all the same, owner name, owner ID, and owner address. But in this table, there's a transitive functional dependencies. You might be able to see it. So if I know the parcel ID, I know the alderman. If I know the parcel ID, I know the township. But if I know the township, every time the township ID is 12, the name is the same and the address is the same. And you can see why that is. I have a township ID and these things that are dependent on it. And I may have different ways of organizing these data, but if I know the township ID, I have this stuff, I could really hive this table off, perhaps, right? So I could have this column here and hive this table off into another table to get rid of this transitive functional dependency. If I know this, I know these. So I would keep this here and then create a table that has just the township ID and the township name and town hall address, would have these records in it, right? So if I know this, I know this, but if I know this, I know this. So if I know the parcel ID, I know the township ID, but if I know the township ID, I know the name and the address. So that's a transitive functional dependency, right? These are directly dependent on this, but they're also dependent on these. So I got to split that table further, right? So this just shows you parcel ID, I know the township ID and alderman, that's a functional dependency. Township ID, I know the township name and town hall address. That's a functional dependency. So this is the definition of a transitive functional dependency. Go back through this if you don't understand that, because it's pretty key here in understanding what's going on, why some of these tables are atomized more than you think they would be. And so I have to split this table up, and again, I split it into these two tables. Now I can connect them back simply through a link or a join from this township ID to here. If I want to find out what are the addresses or names of the townships for parcels, and I can find out who are the owners for parcels by connecting from here to here. So these are my tables in third normal form, all right? First I denormalize them. First I redundified them, went from unnormalized to first normal form. I got rid of the redundant columns. Then I went to first normal form by making everything dependent on a key in a table, and then I got rid of the transitive functional dependencies. So I got one table, I split that table up to go to second normal form, and then I split those tables up as needed further to go to third normal form, right? So here's my split the tables. Now I could split another way. I could say township ID, township name, town hall address, alderman, and this is valid depending upon what the true functional dependencies were. if I only have one alderman for a particular township and township ID, right, so that there's a person and the lines for their alderman district follow a township and township ID, then I'd split this way. But if I don't, if I could have multiple aldermen associated with a township, but the aldermen are split to be associated with the parcel, right? So there's two aldermen, one's the west side and one's the east side of a township, then I'd have to put it here. So again, that goes back to my admonition earlier about it depends on the structure of the data and the universe of things that happen out there with your data. The functional dependencies I see in one data set, like in this toy example data set, it'd be valid to split it this way or split it this way. But it depends in real life how these aldermen are signed. If there's one alderman per township, then it's going to go over here. If there can be multiple aldermen per township, but only one alderman per parcel, then the alderman goes here in this table. So again, how the data can occur in the world, the universe of possibilities, is going to decide or define how you create your tables, your land records tables. So that's about it for normal forms. Remember, there are bad things in relational tables, right? Repeat or similar variables. You don't want to repeat the parcel and owner number, or my earlier example of the parts that go with an order. You don't want multiple dependencies per record, right? So we split those up, repeating records in many blank cells, and we get rid of those if we go to third normal form, all of these things, right? So no repeat columns. Split the tables so that they're all non-key attributes dependent on a primary key, and then further split if there are any transitive functional dependencies. So that gets us to third normal form. In most data sets you'll see will be in third normal form, distributed in third normal form. So it's a little bit of a complex topic, especially for an introductory class, but it helps you understand what the keys are, how they're developed, and why it's so important to identify what the keys are and join in the correct direction.